This is a demo of the photoelectric effect using Einstein's pony, which is a very artfully constructed apparatus to demonstrate it. So you can see the high quality craftsmanship. So what we've got here is an aluminum plate, and that is connected with a couple copper wires coming out, and you've got this little metal foil basically down there, and we're going to put a charge in it. And the other thing that we have up here is a UV light source, and it's got shortwave and long wave switch. And so remember what the difference is. So shortwave, that's high energy ultraviolet photons, and long wave, that's lower energy ultraviolet photons. Now we're going to charge the metal foil by taking a plastic rod that has been rubbed with silk, and it obtains a negative charge, excess electrons. And so we're going to transfer those electrons from the plastic rod onto the little metal foil. And you can see, if you look very carefully, that the little metal foil, they're all repelling each other. And the reason is, once they become charged with excess negative charge, well, like charges repel. And so now this thing has got excess negative charge on it. And so what we'll do next is we'll take that UV lamp on top, and the first thing we're going to do is shine long wavelength UV light onto the surface of that aluminum. And you can see that nothing has really happened. But let's turn on the short wavelength. And you can see all the little metal foil pieces just relax down. So what has happened there is that the long wavelength, according to the Einstein-Planck theory, corresponds to photons of lower energy, long wavelength, low energy. And the short wavelength UV light is higher energy. Now, when you shine the high energy short wave UV light onto the back of the horse, onto that aluminum plate, it actually, each one of those little photons is a packet of energy with enough energy to break the electron free from the metal, and it actually gets ejected out into the air. And so when that happens, that aluminum plate on the back is losing electrons, and electrons from the metal foil on the head of the horse and the tail will migrate in to balance out the charge. And now that they're no longer excess negatively charged, they are not repelling each other. So that's a direct application of the photoelectric effect. The fact that we can see a difference in the energy of those UV photons in short versus long wavelength, and the fact that we can understand that it has to come in packets. It wouldn't matter how long we shine the long wavelength on there, it would never have enough energy to knock off an electron. It's only when you shoot a big enough energy photon bundle at the aluminum that the electrons are knocked off and the foil is no longer charged. So this is a demonstration of the photoelectric effect. So what you can see on the left-hand side is I've got three lasers, one red, one green, one blue. And the interesting thing about a laser, of course, is that they're very specific as to only shine one wavelength of light. So it's a very specific red, green, and blue. And on the right-hand side, you can't see it very well, is a piece of glow-in-the-dark paper. And it's kind of like glow-in-the-dark powder or glow-in-the-dark paint that you can buy. And I wanted to show you that you have to get the right size packet or photon in order to excite this. Let's just take a look and see what happens as I drag these three lasers across the paper. So you'll notice that only the blue one causes the pigment in the paper to glow. And it doesn't matter how long I shine a red light or a green light onto this paper. Every one of those individual photons of red and green is just not enough energy to excite the electrons in the glow paper up to a higher energy state. And so they're just not absorbed. But the blue one, well, that is blue light with blue photons that are high energy, and they have enough energy apparently to excite the electrons in whatever the glow powder is, to have the electrons be excited to a higher energy state, and when they fall back down, they give off this green light. So this is an example that kind of gives evidence that light also, in addition to existing as a wave, is existing as a particle. Each particle of light is a packet of energy of a specific quantized amount, and like I said, we can sit here all day and the red and green will never have enough energy to excite the paper. So we also have a test tube full of glow powder that you can buy commercially and just mix with paint and make your own glow-in-the-dark stuff. It's actually the same material that's on that paper. And I'm just going to show you that I've got this tube and I can just drag the colors across, and you can see here I'll shine that green light on there just for a long time and it just cannot excite those electrons. But here's some blue and the red doesn't do anything. So this is a tube of glow powder, and I can also, you don't have to have lasers, we have some LEDs. So here's even more colors, and we can look again and see if any of these colors can excite this glow paper. And they're not as bright as a laser, but let me move it down here. I think you can see that only the blue photons have enough energy in the packet there to excite the electrons. So like here, only the blue. So this is also the concept of other things that fluoresce. And there are a lot of natural molecules that you might find that will be what is called fluorescent. And fluorescent just means that that material can absorb light of one wavelength and give off light of a different wavelength. That's kind of what you're seeing on this green paper. So we excited it with a blue light, and when the electron fell back down, it didn't give off blue light. Some of the energy was given off as heat, and some of the energy is given off in a smaller size photon, which is green, which is lower energy. It just depends on the type of molecule. But here's another interesting one. I've taken the label off, but this is a bottle of tonic water. So the next time you're having a party and you're making gin and tonics, first of all, tonic water has a molecule in it called quinine. And quinine is a molecule that fluoresces if you shine ultraviolet light on it. But as I'm going to show you, if you shine red or green, the photons are not energetic enough to excite it. So let's see if we can see a difference. So here I'm shining the 3 different lasers through this bottle of tonic water, which has the molecule quinine dissolved in it. And we're trying to see if any of our photons have enough energy to excite the quinine molecule and cause it to fluoresce. And actually, so at the top is red, and at the bottom is blue, and in the middle is green. And I think you can really clearly see that the blue one is able to actually excite the quinine. The blue photons are the most energetic, and they're causing the quinine molecule to absorb that photon, and then when it falls back down, the electrons fall back down to a lower energy level, they actually emit a different color because, as I mentioned earlier, some of the energy is released as heat, and some of the energy then, there's less of it left, is given off as sort of a kind of a yellowish green photon. And the thing you should pay attention to is that when you look at that beam going through from the blue laser, it's not being blue light that's scattered, it's a different color altogether. So that means that it's not just reflecting off so that you can see the laser beam, but it's actually interacting with the molecules in there. There's a chemical change in the electron energy, and the electrons are emitting light when they fall back down. So that's fluorescent quinine water. I have another one here. This is pumpkin seed oil. First of all, there's a lot going on here. But the red one that's shining through, pumpkin seed oil by itself is kind of a reddish orange, and so it's actually just scattering the red light. It's not fluorescing because of the red. So pumpkin seed oil is a mixture of many, many different compounds. And so it's not actually a true solution. So there's light scattering going on, and that's what you're seeing with the red. But you can see the green and the blue, the lower 2 colors, are actually giving off different colors than what they are as they're shined in. So the green and the blue give off kind of this yellow fluorescent. So apparently in pumpkin seed oil, the energy required to excite the electron is at least green or above in terms of the energy, right? So green is less energetic than blue, but that apparently is enough. The fluorescence is the same. They both fluoresce with the same color. But again, the red is not fluorescing. It's just being scattered. If it was fluorescing, it would be a different color. So pumpkin seed oil is also an example of how light exists as a particle, photons. So this is that bottle of tonic water, which has the quinine in it. And this time I'm exciting the quinine not with a visible light, but with, I've got an ultraviolet lamp underneath it. And you can't see that ultraviolet light normally because our eyes don't pick it up, but that glow that you're seeing in the bottle, that's that same fluorescence that we got when we shine blue light through it. And so I can pick up my blue laser and show you a beam. So if you look carefully, it's about the same color, but again, that is the characteristic color that the quinine molecule releases when its electrons are excited. So it doesn't matter, again, you can have more than enough energy in a photon and get it excited, but you can't have less than enough energy for a photon. And so again, that gives us evidence that light exists in little packets of energy called photons.